Welcome. I'll cross my fingers. Hope you're out there. All right, good to see some of you. Um, yeah, so I want to get started. Thought someone might be coming from the Learning Resource Center, but I don't think they're here yet, just to talk about some of the services available there. So the plan for today, I want to wrap up the worksheet that we started working on last time with conditional probabilities, worksheet 2, and then we'll work through the first part of a worksheet on discrete random variables, which you did a little bit of reading about last time. So just to before we get started, I do want to there was a question last time about the quiz, and the first quiz from last time about how it might have been graded. I don't think there was an error on the quiz. So I just want to make sure that that it was graded properly. Sorry, let me just show you the answers to it.
Yeah, I was the one who thought I had it wrong, but it did show the tolerance.
Okay, yeah, that's right. So I might have just chosen a convenient tolerance that if you got it wrong, you might have gotten it right. But yeah, I think it was this last problem. And yeah, technically the answer should have been 0.1767. Yeah. Okay. So are there any other questions before we get started for today?
Yeah, I had a question on the homework that's due tomorrow.
Okay.
When we're, doing the probabilities, is there a number of decimal places you want us to report the answers to, or is that kind of not important as other things?
Yeah, I suppose it's important. Sometimes you're welcome to leave your answer as a fraction, I suppose, in some cases. If you're gonna give it as a decimal, we'll say like 4 decimal places should be sufficient.
Okay. All right, cool.
Yeah, and so that homework assignment, don't forget, is due on tomorrow evening at 11:59. At some point, the homeworks are going to shift back to Monday, I think, but for now, we'll keep them on Thursday. So next homeworks will be due a week from tomorrow, and that will be on the stuff we talk about today and the stuff that we talk about on Wednesday. On Monday of next week. Yeah, and then otherwise, I'll get the rest of the materials for next week's classes up in a module sometime over the day tomorrow and Friday. Yeah, anything else? Okay, so let's pick up with where we left things last time with worksheet 2 with the conditional probabilities. And we were exactly working on, I don't know if I froze for a second. We were exactly working on that problem with the tuberculosis data in that 2A. Oh, no, sorry. We were doing the breast cancer example. That's right. So we were working out. This is where we left it last time. We were first thinking about dependent versus independent events. And then we finally got down to E, which was a conditional probability. And so just remember that when we're asked, in this case, given that patient has a positive test result, so now this is given information. So out of the women who have a positive test result, what proportion of them would actually have breast cancer? And so in that case, that's called a conditional probability. We're not looking at the entire sample space, but rather we're just restricting ourselves to the subset of the sample space that had positive tests. So that changes. The denominator is no longer all 1,000 people, but just the 58.5 people that had a positive test. Any questions about where we left it last time? Okay, so then the big theorem for these conditional probabilities is if I want to calculate the probability of a given B, and so just keep that in mind. That's how we would, if we wanted to say it, how would we express that in words? It's exactly this. What is the probability of A given B? we calculate the probability of A and B, and then divide that by the probability of B. So here, we're only restricting ourselves to the given condition of B. So the given condition comes second, and you can think about this as like, this is like the bottom of the denominator when we calculate this fraction. And so if we take this relationship over here and come back to saying like, well, in general, how do I calculate the probability of A and B? We could multiply both sides by the probability of B. And we see that here's one formula for calculating the probability of A and B. And by a similar rearranging of terms, you could also calculate it this way. So this would be like the multiplicative rule. Which says, right, for example, the probability of A and B is equal to the probability of A given B times the probability of B, okay, or you could write it out like that. And it's only the special case that we talked about that is, if A and B are independent events, then that's the special case where we could just take the product of the two probabilities. So if the events are independent, then we don't need to worry about this conditional probability here. We just take the probability of A times the probability of B. We should assume, without knowing otherwise, that they're not independent, and then we would want to use this general rule over here. So kind of another way that we could define independent events would be to say that two events are independent if this probability equals that probability, if it doesn't matter whether or not I use this or this. So that's another way that we could define independent events. Any questions?
Yeah, could you also use the additive rule to figure out the intersection? Would that be another way?
So you could, so yeah, so let me get a clean page here. Yeah, so so here's the additive rule in general. And here's this multiplicative rule that we just talked about. In general. So yeah, I mean, depends on what you're given, right? So if you're asked to find P of A intersect B, like if you happen to know what this and this are, then you can find it, right? You could rearrange things. But if you don't know what the union is, then that additive rule wouldn't help you, and then you might have to use this. So it really depends on what do you know. If I know this and I know this, then I can figure this out. But if I don't know this, then maybe I need to track down some of these other things. Yeah, so there are different ways that we can do it, and it really depends on what information you know. So just to kind of wrap this idea of independent and dependent up, we kind of started with saying two events A and B are independent, if the occurrence of one doesn't affect the other. So this has no effect on the likelihood So that's kind of intuitively what we're looking for. So for example, the test result of a breast cancer screening and whether or not somebody has breast cancer, we would hope those are dependent events because we would hope that the likelihood of a positive test increases your odds of having it, a negative test decreases your odds, or else what's the point? And so I think the way that we set it up top really gets at this idea. In other words, two events are independent, A and B, if this is true. And this is really saying the sentence that we have above, because this is saying probability of A given that B occurs is just the same as the probability of A if we didn't know whether or not B occurred. So this is saying whether or not B occurs does not affect the likelihood of A occurring. So there are kind of different ways of thinking about it. I think this is a pretty good working definition for independent events. And then again, if they are independent, then you get this special case of the multiplicative rule, where you can just take the product of the two probabilities. Any questions? Okay. All right, so let's kind of crank it up one last level for conditional probabilities, and then we can start thinking about random variables. So remember what a partition is. We say that a bunch of sets are a partition of the sample space if the intersection of any two of those sets is empty, so they don't overlap with each other, and the union gives us the entire sample space back. So for example, all students, freshmen, sophomores, juniors, seniors would be a partition. Taking them all together, we get all students. There is no overlap in those. So if we have a partition, we can think about writing it like this, right? Each of these A's don't intersect each other. When we group them all together, we get the full sample space. And so inside of here is this set B. And so the idea is, well, how could we calculate the probability of B? So I can think of each of these as like little mini sample spaces. And so I could calculate the probability of B intersect A1 using the multiplicative rule, that I could take the probability of times that, right? That's the multiplicative rule. So we take the product of the probability of A1 times the conditional probability. If we happen to know that, then we could figure out what this area is right here. And then we can do the same for this little sliver right here. right? And altogether, what we're trying to accomplish here is like, how do we find out what the probability of B is? If I happen to know some conditional probabilities and the likelihood of each of these A's occurring. So I could work my way down this line, right? And then add up all of these areas, and then that's going to give me overall the total area of B. So over here, we could summarize this by saying we're going to add up a bunch of things that look like that. So the law of total probability says if I want to calculate the probability of B, then I need to add up the products of the probability of B given each of these AIs times the probability of each AI. Any questions? And this is contingent upon the fact that these AIs form a partition of the sample space. If these AIs overlap with each other or they don't give me the whole sample space, then I can't use this theorem. So we've got a partition. The A's represent a partition. And so from that, we can get a more general formula for Bayes' theorem. I'm not going to ask you to kind of memorize this formula, but I do want to see like how we can apply it. So we saw how to do things when we had a partition of the sample space, in this case, the 1,000 women that went for breast screening cancer. One partition for that set would be you test positive or you test negative, right? You don't get both a positive test result, and if you unioned all of those people together, you would get back the original 1,000 people. So when we looked at the two-way table, it was a little bit simpler of an example because the population was just divided into tested positive, didn't test positive. In example 8, we are working with our sample space is like all computers. And one way that we can partition this set of all computers right, would be Mac, PC, and Linux. I don't know, there might be a fourth alternative, but I'm going to stick in these 3 operating systems. We're going to kind of rule out the fact that a computer might run on 2 platforms. We'll just say, okay, we've got computers, either the computer is Mac or PC or Linux. That's the assumption we'll be working with. And so since that forms a partition, we can start to use that previous result and the result above. We can use Bayes' theorem to calculate B. So in part A, right, this is asking us to calculate, I'll just write that out, right? What's the probability that the computer has a virus? So that's not a conditional probability. And in part B, we've got what is the probability that a computer is PC given that it is infected by the virus. So this is a conditional probability. Anytime you see that, that should be a really strong indication it's a conditional probability. Let me just say that they don't always state things that explicitly, so you might need to read the question to get that inference from it. So this question could just as easily have said, out of the computers that have a virus, what's the probability that it is a PC? So you want to look for some language that's telling you, we are just focusing on the computers that have a virus, and we're going to ignore the computers that don't have a virus. So in this case, we want to calculate a conditional probability. What's going to go in this place over here?
Virus.
Yeah, so we're given that the computer has a virus. So over here goes the given condition. And then we're calculating what's the probability that it is a PC given that it has a virus. And what we could do here is kind of using Bayes' theorem. We could say, well, we could calculate the probability of the PC and virus and then divide that by the probability of virus, right? So here we're just restricting ourselves to out of the computers that had a virus, how many of them also were a PC? That's what this formula is telling us. And so that's great if we have that information, right? And so now we need to kind of think about what probabilities do we have and how can we use that information to calculate the numerator and the denominator of the fraction we set up in B. So I'm just going to write out this given information as probability. So we're told that 50% of computers run a Mac. Oh, no, sorry, 30% of the computers run a Mac. That's this 30% here. We've got PC is 50%. And Linux is 20%. Okay. So I highlighted something in yellow right here. I didn't want all of that. So a computer virus is created by hackers. 65% of Macs have the virus. What probability does that tell me?
You have to multiply it by the probability that it's a Mac.
Well, so I'm just trying to say, first of all, like this 65% is telling me some probability. And the question is, like, what would go in the blank here? Is it a conditional probability? Is it an or, a simple probability?
Would it
Isn't
be
it
virus given that Mac? Oh.
Is it virus given that Mac? I think that's what I heard. What do you guys think?
Wouldn't it be Mac and virus?
Yeah, and so here's where we definitely need to be careful. It's really, really easy to kind of confuse these two things. And so the question is this a conditional or not? And so what we're told here is 65% of Macs have the virus. So this means out of all of the Macs, right, 65% of them have the virus. So that's what this is saying right here. That's right. And so if it were saying something like this would be considering like out of all of the computers, 65% of the computers were Macs that had a virus. That's what this would be saying. And that's not going to be possible because out of all of the computers, we know that 30% of them are Mac. So we couldn't have more computers, more Macs with a virus than we have Macs altogether, right? So that's a really, really careful thing to catch. We definitely need to know what it is that we're given it. And I'll just say, it's real easy to confuse this with something like this with something like that, which way the conditions go or whether it's not a conditional probability at all. And so I'll just say, like, the thing that you're looking for in the statement, it might not always be the same, but you're trying to consider, like, is this referring to a probability of all of the computers, or is this just referring to some subset of all computers? And so since we're only thinking about of the Macs, how many of them had a virus, that's why it looks like this. And so we've got virus given PC is 82%. And then we have probability of the virus given that it's Linux. So that V given L means virus given Linux. Okay, and any questions about how we identified those values? Okay, so any thoughts about what we can do then now that we kind of, I think the first step would be like, okay, I need to, what is it that it's asking me to calculate? So I think it's important just to jot that down and then think about what information would we need to calculate these things? What information am I given? How can I put it together? So any thoughts about what we could do next?
Go to a table.
What's that?
I like using tables to kind of
Okay.
like fill in the missing values.
Yeah.
But if there's a more efficient way.
No. So let me just first say that it makes sense that we want to calculate this in part A because we're going to need that in part B, possibly. So one suggestion was the tables. So in this case, what that might look like, and certainly we could do it. So I think it's helpful to see different ways of doing this. Yeah, PC, Mac, Linux. And we have totals. And really part A, right, is asking us to calculate this. What proportion of all of the computers had a virus? And then once I know that, what was it? The question was saying, if you have a virus, what's the probability it's a Mac? Is that the one? I think. No, it was PC, sorry. So then in part B, right, we're going to need to know what is over here. Right, would be the PCN virus, and then we're going to divide that by the total viruses. So we certainly could use a table, and then we could just like start with whatever we want over here and start to fill it in similarly to the breast cancer example that we did last time. And I think if we had something like this, based on the information that we were given up here, what would be like a reasonable place to start filling in this table?
The total PC, total Mac, total Linux.
That's right. So I think we had like 50, you guys can help me out. Was it 50, 30, 20, something like that? 50%, 30%, 20%. Good. So we can start there. That adds up to 100. And then we were also told things like, probability of the virus given a MAC was 65%. And so how could we use that information to fill out more of the table?
Would that go in the second or that first row under Mac?
That's right. So we could take 65% of 30. Someone have a calculator handy? Okay. That's like 19 and a half by my calculation. So we have half of a computer again. But that's okay, right? Because this is all kind of dependent on, we chose 100 computers to start with, which is kind of arbitrary. And then that would give us, what do we have over here? Like that. And then we could use this other information that this was 82%. And that's going to help us fill in that place over there. If someone has a calculator and calculated these, feel free to save me the effort of
42.5.
Thank you.
On PC.
42.5.
Mm-hmm.
That would be 7.5 over here. And then this one, did anyone get this one?
That one was 50.
50.
So 10.
10 and 10? Oh, it's 50% were of Linux were.
Yeah, sorry.
Yep. Okay. So if you like these tables, this is no different than the breast cancer example, right? Essentially, but we have a third partition here rather than, you know, has it or doesn't have it. Instead, we've got PC, Mac, and Linux. And then we can add this up. So that comes out. Also help me. I did it differently, so I don't have this worked out. What do we get when we add up all of these things over here?
For virus, it's 72.
Thank you. And so
Or,
that was,
sorry, 62. My bad.
sorry, 62?
Wait, was it? Yeah, 62. Or no, 72. My bad.
Okay. This is why I don't do it. I leave it to you. I've got to think and write and speak. There's a lot going on. Okay, so yeah, that works, right? And so now we can say, well, part A was saying, what's the probability of a virus? And now we can see that's 72 out of 100, 72%. Is that right?
It's 62. And the other is 28.
Oh, this is 62 over here?
Oh, no, I'm sorry. It is the 72. I don't know why. Yeah.
I
forgot the
kept
10.
forgetting about the Linux. That's why.
Okay, I'm trusting you guys on the math, so please let me know if there's something seems off. Someone got something different. So then in B, right, the probability of, given that it has a virus, that it is a PC, would be the 42.5 out of the 72.
Hey Adam.
Yeah.
I think it should be 41 over 72, not 42.5.
This one was calculated wrong over here. Is that the idea?
Yeah, it's 0.82 times 50%, so it should be 41.
So this should be, yeah, so this is 0.82 times the 50 is 41.
Yeah.
Whoops. I should be checking this. It is 41. Thank you.
Okay.
Yeah, sorry. Let me just fix that. That's going to affect this over here too. So that makes that a 9. And then let's make sure all of this is added up correctly. 41 plus 19.5 plus 10 comes out to 70.5. So sorry, we updated this, we updated that. So down here, it's going to be off a little bit. So sorry, what am I doing? So we've got 70, I see, sorry. So the probability of a virus is the 70.5 out of 100, which is a 0.705. So this is telling us that about 70% of the computers had a virus. Sorry for the arithmetic there. Did everybody catch up? Sorry with the error. Yeah, so virus would be this total out of this total over here. So this is not a conditional probability, so we're considering out of all of the computers, 70.5 of them had a virus. And then over here, we now have 41 out of 70.5. So that's like 58%.
I have a question about that. It's kind of minor, but I was just wondering, like, if you didn't want to say, assume 100 total and then work from that, like if you're given percentages, could you just use the percentages and then like have them all add up to 1? So like you could go do like 0.5, 0.3, 0.2, and then your total would be 1. Like,
yeah, so that's right. Let me just copy this table.
Because it should work out the same way, like if you're taking,
that's right,
a percentage of like a fraction.
Yeah, so if instead of saying 100, we had 1, right? You guys can see my screen, right? I mean, I have so many things open here. Okay, I don't need to see. So yeah, if instead we had 1, then it's like shifting the decimal of everything, right, over here. We kind of get back to where we started. That's right. So we could have done this. We didn't need the table. I think the table is particularly nice as well because it connects back to what we did before. But if you just want to use the formula, we could have used the fact that the probability of a virus, we could write using that the law of total probabilities as the probability of a virus given PC times the probability of a PC plus the probability of a virus given a Mac times the probability that it's a Mac and that would give us exactly the same result over here. I'll just say that. That would exactly, right, how we got each of these totals over here was taking this times that and taking that times that. So let me just say this would give us the same exact answer. Okay, which checks out above. So you're certainly welcome to use that formula and just go through it directly. If you want to set up the table, that's another way to do it as well. That's good. So at the end of the day, the main point here is they're doing the same thing. So if you're comfortable with that, then we've got the main idea here. Any other questions? So I'll just say, okay. So let's bring it back to the Monty Hall problem where we started things last time. And if anybody is curious, kind of the first class we started with the birthday problem, and then the very last question on that worksheet was, let's do some math with the birthday problem. So if you're curious about that, I did put the solutions up in that. And we had a match in January, which was very anticlimactic. I like it when we get the match in December for the matching birthdays. But if you check the math, there was a 70% chance that we would get at least one match. So you can see how the math works there. For this problem, for the Monty Hall problem, I don't think it's going to be particularly useful to write out a two-way table. But let's think about the sample space here if we want to try and rationalize this. So remember, we have three doors. We have a door number 1, a door number 2, and a door number 3. And so we think about the sample space, the different ways that we can configure a car and 2 goats would be either the car is behind door number 1, or the car is behind door number 2, right? Or the car is behind door number 3. And the question is, we kind of saw this experimentally, that the people that were switching were winning about 2/3 of the time, and the people that were staying were losing about 1/3 of the time. So if you think about it, you pick door number 1, you stay after they open up a door. The opening up the door in between didn't affect the odds at all, right? It just is like, you pick door number 1, you have a 1/3 chance of being right on your first guess. And that's why we're seeing that 1/3. But let's just consider this. Let's see, given that the person switches, let's see how likely they are to win. So let's, without any loss of generality, let's just assume the person chooses door 1. So they choose, for example, if this were the setup, they choose the car, game show host opens up a door, maybe this one over here. This person decides to switch. What's going to happen to them? Are they going to win a car or not?
Not.
Right, they got the goat. So in this case, switching was a loss, right? You picked the car, but then you switched after they opened up the door. If this is the setup over here, and again, this is the full sample space, right? There's only 3 ways to configure these. I pick door number 1. The game show host is going to reveal that goat, take that out of play. If I switch, what happens?
Win.
We get a win. And similar story here. We pick door number 1. Game show host is going to reveal that goat. You switch, you get the card, and you win. So that's 2/3. I'm just approximating that. And this analysis would have repeated exactly the same if we said, what if they chose door number 2? What if they chose door number 3? So that fact doesn't really have any effect on the calculation here. So short story is, it does definitely make sense in the long run to switch every single time. Though you're not guaranteed to win, not 100%, your odds are better. That's all you can hope for. Any last questions about conditional probabilities? Okay, so then let's move on into the next worksheet. So this is kind of worksheet 3A. I broke worksheet 3 up into 2 pieces. So this deals with random variables. So I think part of this hopefully went through in the video. Random variables are actually a really weird name for what it actually is. It's not random and it's not a variable. That's the confusing part, but yet we call these random variables. A random variable is a map. That's what you should think about it as a function, which is strange that we call these random variables. So it's a function that maps from the sample space into the real numbers. So the example in the video was like shipping 10 batteries, right? And each of the batteries is either defective or it's fine. We could write out the sample space as a bunch of a string of D's and G's, and then we can say the random variable is the map that sends this outcome to the number of good batteries in the shipment. Okay, so here was what you guys thought about on the quiz, which was a question about a quiz. That was like a very meta quiz there. So, you know, what is the sample space here, first of all? So someone want to chat in, like, what is something that would be in this sample space? So now let me just say again, we're taking a quiz. There's 3 questions on the quiz. Each question has part A, B, C, D to choose from. So the outcomes here would be how the student does on the quiz, right? So what are the possible outcomes for this student?
All right.
Sorry, Derek, what'd you say?
All right answers.
Yeah, so we can say correct, correct, correct. What else?
All wrong.
All wrong. So I'll use W for that. And other various combinations of C's and W's, right? So it's pretty similar, except we've got correct and wrong instead of good and bad batteries. And the odds of being correct are 25% here. And so on. So I think we should have altogether 8 different things. Right, CCC. I'm not doing this in the most systematic way. I think that's all of them. Should be 8. 1, 2, 3, 4, 5, 6, 7, 8. I must have written one of them twice.
Yeah, the last one.
This one is here and right there. Yes, thank you. Yeah, so there's 8 of them. And the thing that's really, really important to note here is that, you know, if I ask, what's the probability that you get 100% on this quiz? So I'm gonna, if I just change this a little bit and I were to say, I'm gonna think optimistically, X is the number of correct guesses. So our random variable here is mapping each of these strings to like how many C's occur in it. And so what you wouldn't want to do here is say, this is 1 out of 8, because out of these 8 outcomes, only one of them is all correct. And the difference is we're not picking people out of a hat anymore. Each of these outcomes is not equally likely. So we don't want to just count up how many outcomes are there, how many outcomes are in my event. We need to take into account that each of these outcomes has different probabilities. So what would it look like for X equals 0?
Is that 0.75 cubed?
That's right. So we could say 0.75 cubed, and that comes out to 0.422. So I'm going to fill this in on the table below. So on the table below, we've got, okay, here's the value of x, here's the probability that that would occur. So what we see here is, you know, this is the probability of getting those 3 W's. So let me just kind of highlight that. So that's where the 0.42 comes from. And if I wanted to do x equals 3, right, then that would be the 0.25. Because these are independent events, I should just explain, right, that's where those products are coming from. It's 0.25 times 0.25 times 0.25. So we do have this assumption that a student's guess on question 1 has no effect on whether their guess on question 2 is right or wrong. So that comes out to about that. So that's how likely that is, right? So that's why we don't want to say the odds of getting everything right would be 1 out of 8, because that one outcome is very unlikely to occur. Okay, and so if we want to calculate the probability that x equals 1, we now need to be careful that there are multiple ways that that can happen. So here would be x is 1, right? We're just looking at what are all the outcomes that had only one C in it. And those are the 3 that I highlighted. So then we could say, what's the probability of this and we can use the independence to take the product. And that gives me the probability for that one outcome. And then I need to multiply that by 3 to take into account there are 2 other ways that we would get that same result, and all of those are the same probability, right? Because the ordering isn't going to affect the probability. And I'll just kind of wrap up with x were equal to 2. We would follow this very, very similarly. So this would be what's called the probability distribution for the random variable x. Oftentimes you can write these in a table. And notice when we add those all up, that gives me 1. That's good. And so one point to note here is that this example is what's called a discrete random variable, because the values, the output of the random variable is 0, 1, 2, or 3. So a discrete set of values. We will run across continuous random variables, which could be like you pick a book out of the library, you know, the random variable is going to be how much does it weigh, or something like that. So that we could attach a number to each outcome, which might have decimal values and other things. So when we're measuring things, typically we're going to have a continuous random variable. When we're counting things, we typically have a discrete random variable. So each of these things, this tells me you know, what is the probability of getting nothing right 42%-ish? What's the probability of getting exactly one answer right? It's the same, and so on. Sometimes we come across things like this. So this is saying, what is the probability of getting at most one question right? Right, and so for that, we would just add up probability that it's 0 and the probability that it's 1. So that would be 0.844, 84% chance. And this is what we call a cumulative probability. Where we're taking what is the probability of at most. So when you see an at most, or you see less than or equal, that's telling us that we have a cumulative probability. Any questions? Okay, so that's right. So here we've got probability distribution function. I'll just say sometimes these are also called probability mass function when we have a discrete random variable. So these also might be abbreviated with a PMF instead of PDF, but they are the same. So this tells us the probability of getting exactly X, whereas over here, this is telling me the probability of at most X, at most 1 correct. And this we call a cumulative distribution function. This gets abbreviated with a CDF. And so, you know, these are functions. So we like to write them out as a formula when we can. Oftentimes we can't, or we can graph them and then study kind of properties of the graph to see what sorts of properties the distribution might have. So when we sketch a PDF for a discrete random variable, we're just going to come over to 0 and say, okay, what was the value? What was the probability of getting exactly 0 questions correct? So let's see, 1, 2, 3. I have a scale here on the axis that should line up. I'm just going to call this 0.1, 0.2. So when we were at 0, we were about there. When we were at 1, it was the same value. That was about here. And all I'm doing is just plotting each of these values that we had in the previous table. So I'm plotting a point at 0.442. So we're kind of reading X as the input, the probability that we get exactly X as the output. Right, so maybe we could have something that looks like this. What was 3? That was really small. That's basically close to 0. Sometimes you might see it written like this. Sometimes you might see it written like that as like a step function or as bars. Yeah. So I'll just leave the dots in there. If it were a continuous function, then you would have like a curve, right? That goes through all of these points, but ours is discrete. So if x is equal to 0.5, we don't have any output here. So on this one, we're going to start up here at 1, and we'll go down to 0. I think that's right. 1, 2, 3, 4, 5. Yeah. So each of these ticks is like 0.1. So for the cumulative distribution, here we're plotting the probability that x is less than or equal to x. So we would start at 0.422 at 0. And then if we want to plot the point at 1, we're now saying, what's the probability that x is at most 1? So we add these two together. So I'm approximately putting a point at 1, 0.844. And then at 2, we would add another 0.141. So it might look something like this. And sometimes when we have discrete things, these might be drawn with like vertical bars that come down. I think that's how the textbook does it. But what you want to think about here is this is plotting at most. So what's the probability that on a 3-question quiz, someone gets at most 3 questions right? That's 100%, right? They can't do better than 100. So when we talk about probability distributions, we use lowercase f, and when we're talking about cumulative, we use capital letter, and this is telling us the probability of at most. Okay, so I'm gonna break us up into rooms for a couple of minutes to just think about these properties. Which of these properties is true or false? So in other words, just to like do the first one together, the first one is saying, okay, for all values of x, fx is between 0 and 1. And just to clarify with this notation, this subscript should be referring to the letter that you used for the random variable. So in this case, we have a capital X. So this is really telling us the probability distribution of random variable x. So what do you think? Does this seem true or does this seem false? Give me a thumbs up, thumbs down. Yeah, that's true, right? Because this is a probability. So this is really saying what are the bounds for the probability of the random variable being exactly equal to x. It has to be bigger than or equal to 0. It can't be more than 1. So that's all I'm asking you guys to do kind of in your groups is kind of just talk through some of these properties. Think about whether they seem true or not. That might be from a practical point of view of interpreting it, we've got nice graphs above. You might think about what the graphs would look like to match these up. So let me open up some rooms. And okay, you should see them opened up, and let's plan on taking like 5 minutes to just kind of talk about whether these are true or false. So nothing to solve here, just, you know, do you think it's true? Do you think it's false? All right, good, I think everybody is back. Just gonna take, this is what I like about Zoom. I can just take attendance by taking a screenshot. That's all that's happening. You're here. Okay. Yeah, so was able to talk with 2 of the groups. Obviously I missed what happened in one of the groups where you was, but just to kind of summarize what came up, we had a true and a true because these are probabilities. So they can't be more than 1 and they can't be less than 0. This was true because if we think about adding up the probability of exactly 0 plus exactly 1 plus exactly 2 and so on, we get the full sample space. So this is equivalent to saying the probability of all of the outcomes is 1. That doesn't work over here because these are cumulative probabilities. So this is like saying what's the probability that x is less than or equal to 0 plus the probability that x is less than or equal to 1. And when we do this, we're double counting outcomes, right? Because the probability of 0 would be included in every single one of those. And we also saw that wasn't true in the example that we did up here. So this is definitely false. The sum of the values doesn't give me 1, but the limit as x goes to infinity does give me 1, right? So part F is really saying, what's the probability of getting at most infinity, okay? And that should be 100%. You can't get more than the biggest possible value. However, that's certainly not true over here. And we saw that. In this case, the limit as x goes to infinity is actually going down. And this is non-decreasing is false. Whereas the cumulative one being non-decreasing is true because each time we go from here to here to here, we're including more and more outcomes. So it has to at least be staying flat at minimum or going up. Yeah. So that's good. So these are some general properties for PDFs and CDFs to keep in mind, at least the ones that are true. Okay, so sorry, we're out of time. So for the video on that will be for Monday, actually will be kind of like laying some of the groundwork for the next worksheet. So we'll finish this stuff up together tomorrow, or not tomorrow, on Monday, and then move on to the rest. And we will be using R in class to some extent. So definitely please try and get that R and R Studio installed over the weekend so that on Monday you'll be ready to go. And if you have any trouble getting that installed, just reach out to you or myself. We can help you with that. It's all free. Please don't purchase anything anywhere. All of this software should be free. So if you're asking you to buy something, you're downloading the wrong thing. But the instructions are up in Canvas. And if you have questions, I've got office hours tomorrow, 10:30 to 11:30. Otherwise, have a nice weekend. Good luck with your homeworks, and I'll see you all on Monday.
Thank you.
Thank you.
Thank you.
Mhm.